Hello and welcome back to Things Made Simple. This is my YM3812 modular synthesizer on a breadboard. It's a little different now though because it has two YM3812 chips. But guess what? We're actually not going to talk about that today because while I was working on this, Juanito from Modular for the Masses totally nerd sniped me with a Roland 909 side quest of epic proportions. But rather than describe it myself, I think I'll let him tell it to you in his own words.
Good morning.
Good
This
morning.
my
Yeah, I've already had all three of my cups of coffee, so.
What do you drink in a can? What is that?
Oh, this
That's
is
not
like La
coffee.
Croix. It's just
Oh, gosh.
sparkling water. Wait, so you've got an idea? What's your idea?
Well, back in the 80s, when the 909 was designed, memory was so expensive. Computation was so expensive. They do have a computer in the 909, but it is a very simple microprocessor that can do the sequencing. That's all the computer in the 909 is doing is the sequencing. There's no audio processing at all with
Okay.
the computer inside the 909. And synthesizing symbols is incredibly difficult. The 808 symbol sounds are synthesized using a sort of shimmer type of sound, which is in the 808 case, it's a CD40106 chip, which has six inverting Schmidt triggers. Those inverting Schmidt triggers are used as oscillators, and they're all running at a certain frequency. And it makes this noise like the shimmer noise. And that noise is passed through a VCA and some filtering to get the ride and hi-hat. There's no crash cymbal on the 808. It's just the
Right.
cymbal and the hat. And that the 808 was heavily criticized for having really strange sounding cymbal voices. My favorite might be the 808 cowbell, which is ludicrously stupid sounding, but it's two of the oscillators from the cymbal shimmer sound just going boom. It's nonsensically bad, but it's iconic. It's great for what it is.
Totally.
But that strategy was not really workable. So when they were designing the 909, they decided to ditch the synthesis method and use samples instead. But everything was so expensive, so they just used 6-bit samples from this chip to get a sample of a cymbal and a hat. And it really is. I mean, you listen to it and you're like, yeah, that's a sample. That's not a synthesized sound. The 909 cymbal, hi-hat, and crash cymbal, ride cymbal, hi-hat, and crash cymbal are made with a 32 kilobyte read-only memory chip.
Okay.
The way these voices work is you trigger them, it starts a counter running from binary 0 up to whatever address it
Mm-hmm.
needs to be. It feeds that address into one side of the pin, one side of the chip. Out the other side of the chip comes the data that's on the chip.
Okay.
That runs through some resistors and turns into sound. It is a sample player that has no computation going on. I mean, it's not analog because it's digital, but it's
Right.
as close to analog as possible while still being digital. For the ride cymbal and the crash cymbal, there is a sample speed dependent envelope. I believe what's going on is that as the cymbal sound decays, if you use that cymbal sound and let it decay in the sample, you're losing the ability to make a realistic sound. So they kept the sound quite loud to preserve fidelity, to preserve the bit depth. So then that doesn't sound right for a cymbal just to be the same loudness the whole time. So they have a decay envelope built in that's going, that's tapering the cymbal sound away. The hat, which is the module we're going to work on,
Okay.
doesn't have that. It does have an analog decay envelope, just kind of as part of the circuitry. It also has a little bit of low pass filtering in there, a 4-pole filter with transistor buffers. So there is quite a bit of analog synthesis strategy going on in the voice, which makes it so that if you plug there's a amazing sample players out there that fit into synthesizer EuroRack.
Yeah.
One of them is the Tip Top One. You could just put a 909 sound in there and you've got a facsimile of the 909 sounds. But as a lover of dance music and techno in particular, I've wanted for years, I've wanted to get this voice in my synthesizer.
It sounds like it's kind of like a hybrid then. It's the digital piece plus some like analog magic that shapes the sound with an envelope and a filter and VCA, that kind of thing.
Yeah, that's exactly right. Mm-hmm.
Okay. So it's not as simple as just a sample. That's cool.
Not as simple, no.
Okay. So what's the idea?
Well, the Roland cymbal voices are using 6-bit samples. And so I was realizing as I was building my modules inside of tin cans, I was like, wait a second, this is a 6-bit sample. The sample would technically fit in an Arduino's memory, but there wouldn't be any room for the program. So you could take that 32 kilobyte sample, discard the unused bits, 2 per byte, and then you would end up with, I think it's 4 kilobytes. That might be right.
24. So yeah, 3/4 of it. So like
Yeah.
24 kilobytes instead of 32.
So you could shrink your sample down, then you would have enough room for the program. So I thought about that. I already had 909 sounds in my modular, so I didn't think about it super hard. But then one day I was thinking, hey, maybe I could offload this this puzzle to somebody else who's smart, somebody clever. And so I sent my friend Tyler a message. I said, hey, I was thinking about this. And he was like, okay,
let's do it.
Off to the races.
Yeah, no, that's awesome. Okay, cool. Yes, I think we can pull this off. So there's this website here, colinfrazier.com. And this person actually went through and extracted everything, actually built this really sweet looking 808 909 clone here, and then pulled together some exports of the actual original ROM files, and then he turned those into WAV files.
Yeah, this is the site that I used a ton of his resources to build my 909 voices.
So if you click on this.
Yep, that's it.
That's the one? Okay.
That's the one.
Let's take a step back and talk about waveforms. When sound waves are recorded by a computer, the vibrations are turned into voltages. In this case, the voltages are measured on a scale from 0 to 63. As the waveform changes, the voltage level is measured thousands of times per second, and those measurements make up the data that represents the waveform. All of this data is then saved into a file called a wave file. If you've ever wondered what goes into a wave file, it's actually pretty simple. The file's divided into a few chunks. The first chunk, called the riff chunk, includes information about the whole file, like the size and the format. In this case, the format is wave. The second chunk includes information about the format of the sound data. This includes things like the sample rate, which is 32,000 samples per second, and the number of bits per sample. In this case, it's 8 bits per sample. The third section contains the actual sound data. The chunk size indicates the size of the sample data, 32,768 bytes in this case, and then after that you get a long sequence of bytes that make up the sample. Now, the 32,768 bytes is kind of a problem because Juanito wants this whole thing to fit on an Arduino NANO, and that chip only has 32,000 bytes of program memory. So in order to fit the sample and the program into PROGMEM, then we need a way to compress the sample. And this is the trick that Juanito nerdsniped me with and actually inspired the project. Right now, the wave file is an 8-bit wave file. And that means that each voltage level is measured on a scale from 0 to 255. And each measurement takes up one entire byte. But in the case of our HiHat sample, we only really need 6 of those. That means that there's 2 unused bits for every byte in the file. If we could only include the bits that we actually use, and then join them together, and then split those back into 8-bit bytes, then we would turn 4 bytes into 3 compressed bytes. And to do that, of course, we need to use a little bit of bit math. In order to actually do the compression of the wave, I created a small Node.js program. And this works great except for one thing. The integers in Node.js are actually 32-bit integers instead of 8-bit ones. And if you left shift a variable, then the top bits don't fall off like they would with an 8-bit integer. Not to worry though, if you AND the output with a binary number of just 8 ones, then you're going to strip off all of those extra bits. So going back to our formulas, we just need to AND them with 0xFF to ensure that the output is an 8-bit number. Okay, so we're going to take that WAV file and we're just going to run this like compression thing on it. And it is going to then produce a couple of files. So it has created this R909HH.h. So let's see if we cat that. H. So it kind of creates like a header file, but it's just a dump of all of the stuff in like one giant array. This will give us a header file that we just compile into the Arduino code once we write it.
Yeah.
The other thing it created was original wave.png.
Mm-hmm.
It doesn't look like much, but if you zoom in on it, it's only like a 32,000 pixel wide picture here.
Oh, okay, sure.
But if you zoom in on it, then you kind of see what
yeah.
that waveform is. And this is just plotting out each of those data points that were in the file. And you can see as you kind of move over that it's getting quieter.
Here comes the closed, there's the closed part.
Oh, there it is. Yeah, that's the closed hi-hat, and then it goes back down to 0.
All right.
I'll go and code the Arduino thing that actually plays the sound, and then I'll show you what that looks like when I've got that done.
All right.
All right, so now we need to make an Arduino program that can output each of these voltages at a very reliable and constant rate. To do that, we're going to need to take advantage of something the microcontroller is actually really good at: counting. See, inside of the microcontroller is a counter. This counter starts at 0, and it increments automatically with every single clock tick. You don't have to write any software to make this happen, it just kind of happens inside of the hardware. That's why it's called a hardware counter. Now, when the counter reaches a limit, it triggers an event, and then it starts over at 0 and keeps counting again. Now, if we were to change the limit, then it would change how long it takes to count to that value, which would then change how often the event triggers. And since the speed that the counter increments is fixed, it's basically the master clock, the speed of the events becomes very predictable and consistent. Now, these events are called interrupts, and they trigger special functions that are called interrupt service routines. Our interrupt service routine is going to do the business of decoding the sample and outputting to a port on the microcontroller. Here's how it works. Every time the interrupt runs, we're going to check a buffer that contains a chunk of decompressed bytes from the sample. If that buffer is empty, then we're going to have to go fill it up. So we'll pull the next 3 bytes off the sample and decompress them into the buffer, using the sort of like opposite bit math that we use to compress it. And then we take the first decompressed byte and output the bits from that byte onto port D of the microcontroller. And then the next time the ISR runs, it uses the next set of decompressed bytes, and then the next one, and then the last one, and then at which point it needs to refill it again with new compressed sample data. Now, to convert this into an analog signal, we're going to take the most significant 6 bits and we're going to run them into a set of 2K resistors that are all connected together by 1K resistors before finally connecting to ground through another 2K resistor. This connection here at the top is then going to provide an analog output that represents the sound that we're trying to create. Incidentally, this type of DAC is called an R2R resistor ladder because it uses a bunch of resistors that are one value and then another bunch that are 2 times that value. Here's a look at the final schematic that I'm using for this. The output of the DAC just gets buffered and then sent through a DC blocking capacitor. But one other feature that I've added is the ability to adjust that limit that our counter counts to by reading the value of another potentiometer. This way we can change how quickly the interrupt triggers, and thus how many samples it plays per second, and that's actually going to affect the pitch of the sample. Okay, let's give it a whirl. All right, I think I've got it on a breadboard now. So let me show you this thing working, and then you can let me know if this actually sounds right. Can you hear it?
Yeah, there's some harsh right there. Yeah, there's some digital problems. There's some artifacting.
Yeah, so this is it on the scope here.
Oh yeah, there's a bunch of positive values that shouldn't be there.
Yeah, it looks like a
Especially when
little weird.
it's right at the fade out of the it's right at the fade out of the open hat. That's interesting.
What do you
What's
think would
going on?
cause that? Like, is it really
No, that's incorrect.
supposed to be there? Like, I wonder if I should just like slice out a piece of the waveform.
I
Like
mean,
only have it go for like a split second or something instead of like the whole thing. Or like maybe
no,
I
we
don't
have
know,
to get
there's
the
like
whole thing. Are you serious?
okay, yeah, you're right.
I
And see if
need
I
you
can
to
figure out what's going on.
manually grab each one of those bits that's too high and pull it down. Just every single one
There's
with
got
your
to be a
mouse.
reason for it though, because like remember when we did the image of the input waveform, it didn't show all that
That looks
stuff in
fine.
there, right? That
No,
looked right.
that looks right. But that was the original image, right?
That was the original wave file. Well, here, let me take a look at what the plot looks like for the compressed one. So I'll write some JavaScript that'll take the compression or the compressed version of the data and then uncompress it and then display that back.
Yeah.
I think we may have found the culprit. This is the same file that was going to go into the Arduino that's been compiled into the Arduino,
Yeah.
but it's been decompressed again. And then now I'm plotting out the new value of each of those points.
Yes.
Okay. And if I'm at the beginning here,
That looks
they look
fine.
okay.
That looks good. That looks fine. No problems. Here, oh, there it is.
There it is. So this seems like a problem.
That's
Uh,
2 rows of bits. Why? I mean, bytes. Well,
Bits, bytes, something.
three-quarter bytes.
Okay, I've gone through the calculations like 10 different ways, and then I'm almost positive that they're right. But I do have a thought. So if I go back to this little presentation thing,
Yes.
one of the assumptions that I'm making is that these last 2 bits are always 0 because that's what they
Oh,
said in the in the website is that he took each of the 6 bits and then he moved them over and then made the last 2 bits 0.
yeah.
And I'm wondering if those 2 last bits are actually 0 all the time.
Well, that would make sense. That would explain if there's a a 10 or a 0 1 in those last 2 places by pure accident. That would explain why the 2 incorrect values wind up being in 2 rows.
Right, exactly. Because if you were to take like, let's say that there was a 1 1 here, and then I OR it with this one, then I would end up getting like one of 2 different outcomes.
Yeah.
Let's see what happens if we go back into the code. So this is where I read the file data. So maybe what I can do is AND this with something that's just the top 6 bits. Let's see, 1, 2,
0
3,
0.
4, 5, 6, 0, 0.
Yeah.
So if I do that for each of these,
Then
then that should get rid of the last 2 bits for sure, right?
yeah, cleaning up each input byte.
So now if we run that, and then let's also have it create that visualization of the debug file.
That looks great.
That looks right.
Yes, that looks good. It's going to sound fine.
Okay. All right, let's give it a
Okay.
shot. Let me compile this into the Arduino and then we'll see what happens here. Better?
Yes, that's perfect. Yeah, that's good.
Okay, so this is now showing both the both samples and it's coded now so that it'll distinguish between the two. So you can push a button to do the long one or the open hi-hat and then another button for the close hi-hat.
There's no enveloping going on or filtering, right?
Correct. Yeah, this is right now just the
Just the
resistor
raw
ladder.
waveform, yeah.
And then but there is the ability to change the pitch. So you
yeah.
can adjust this thing and all that's doing is changing how fast it's playing the samples back.
That sounds perfect. That's what I would have done. Maybe. Now, I notice you're not using an Arduino Nano in there.
Good point. Yeah, so I was lazy and I did not get out, or I had to go find Arduino Nano, but I've been using this particular chip, which is
Okay.
kind of like an Arduino Nano in that it doesn't really need any additional components. It just kind of works. The difference is that it has way more capabilities. It has 128 kilobytes of program space. It's got 16 kilobytes of RAM. It's also 5-volt tolerant, which is great as well.
What's the name of that chip?
It's an AVR 128 DA28.
Ah, lovely. That's a dip package, and it still ends up being smaller than a Arduino Nano development board. So
Oh,
more pins, 28 pins,
yep.
4 times as much memory, I mean
Hmm.
flash, and then more RAM, and it's faster, and it needs fewer external components. Perfect.
Yep. And it has capacitive touch capabilities.
Oh, I will be reading some data sheets about this.
So clearly, this adventure has only just begun. We still need to explore the entire analog section of the circuit, from the envelopes to the voltage controlled amplifier and even the filters. And who knows, maybe Juanito will even dig into those capacitive touchpads. If you like this video, give it a thumbs up, and if you want to see what happens next, be sure to subscribe. But in the meantime, thanks for watching, and we'll see you next time on Things Made Simple.